Dujella. He's from University of Zagreb, Croatia. He's a professor of mathematics there. And, just to tell a few words about why Professor Dujella is so much well known. His work in Diophantine tuples, which is part of his title of his talk today, is very well known. Like people who know Diophantine tuples, he is famous for the work that, there are, if at all there are 5 tuples, there will be finitely many, and there are no 6 tuples. So it ends there. And of course, he's also very well known for using Diophantine tuples for constructing elliptic curves of high rank. And his interest also is there in Diophantine approximations and, elliptic curves, constructing these high rank elliptic curves. And recently he has written a book in number theory. I was fortunate to get a soft copy from Professor Dujella, and I can tell the young students who are here, young people who would like to start just to learn number theory from the basic, this book will be very, very useful. Starting from very basic, you really go into the deep, and I really recommend this book to the people. And certainly in our library, you will have one copy of that one. And Professor Dujella has already, is a very prolific researcher, and has about 14 PhD students under him, has many, thesis advisor of masters, undergraduates and all. He's a prolific teacher. He's associated to all the scientific, agencies in Croatia. And of course, he's the chief editor and initiator of a popular journal in mathematics. So I would request Professor Dujella to begin his talk today. And the title is Triples, Quadruples, Quintuples, which are DN sets for several ends. Professor Dujella.
Thank you so much for a very nice introduction. I would like to thank the organizers for their kind invitation. It is great pleasure for me to have opportunity to speak on this conference with which we celebrate 75th birthday of Michel Waldschmidt. His work is great inspiration for all number theorists. Today, I would like to speak about some recent result on one variant of a problem of Diophantus. I will start with a short overview of results about classical problem of Diophantus, and then I will move to the variant indicated in the title of my talk. So, story started with the following problem, which can be found in fourth part of Arithmetics, a book written by Diophantus. He asked for 4 numbers such that product any 2 of them increased by 1 is a perfect square. And he was able to find one such example, and this example consists of 4 positive rationals with the given property. Fermat studied the same problem, and he was able to find solution in positive integers. It was the famous set 1, 3, 8, and 120, which is probably the best known example of set of Diophantine tuples. For example, if you take number 3 and 120, multiply them, increase by 1, you will get 361, which is 19 squared. And all other, there are 6 conditions here to be satisfied. It is easy to check all of them. Euler made several very important contributions to this problem, and on this first slide, I will mention just 2 of them. So first, he was able to extend this Fermat quadruple with 5th element, 5th positive rational number. And what is interesting that for several centuries, it remained open question whether this extension is unique. Is there any other rational number with the same property? And very recently, Michael Stoll proved that this 5th element is indeed unique. Other result of Euler, which I would like to mention here and which will be used later in my talk, is that he generalized the Fermat construction and in fact proved that there are infinitely many quadruples with the same property, more precisely that if we start with any pair, which is good, so AB plus 1 is perfect square, then this pair can be extended first to triple and then to the quadruple. If we take A equal 1 and B equal 3, we will get exactly Fermat sets. So these examples, I think, motivate the following definition. A set of n non-zero integers is called Diophantine n-tuple if product any two of them is increased by 1 is a perfect square. If elements of such set are non-zero rationals, then such set is called a rational Diophantine n-tuple. And principal question in this topic, this area of number theories, how large such set can be. And in fact, here we have at least two questions. So how large such set can be in integer case and how large such set can be in a rational case. And we will see that the situation is quite different concerning these two questions. First important result concerning this integer variant of a problem is famous result by Alan Baker and Helen Davenport in 1969. They proved that Fermat sets cannot be extended with fifth positive integer. More precisely, they proved that if we fix 1, 3, and 8, then fourth element has to be 120. Usually it is said that that problem was motivated by Martin Gardner column in Scientific American in 1967 and talk by one Lind given on a conference in Oberwolfach in 1968. But a few days ago, I discovered a column in Sunday Times 10 years before, which asked a similar question. So they posed a question to their readers. If we start with 1, 3, and 8, then find the fourth element, and they offer £5 as a reward, and then try to find the fifth element, and they offer the £25 of the reward for finding fifth number, and there were more than 100 correct answers for this first question, and of course no answers for this much harder question for which now we know that there are no solutions. There were several generalizations of this result of Baker and Davenport. So let me mention that in 2004, I proved that there are no Diophantine sextuples and there are only finitely many Diophantine quintuples. And finally, in 2019, He, Togbe, and Ziegler proved that there does not exist a Diophantine quintuple. Here I would like to make one maybe digression to mention two publications, which I think for me and for other researchers working in this area were very great motivation to proceed with our work. So Michel Waldschmidt in 2001 gave a talk in a conference in Pisa, conference on Hilbert's problems today, and his contribution had titled Open Diophantine Problem. And as one of important problems for the next century or millennium, he mentioned problem of existence of Diophantine quintuples. And a few years later, a version of this report was published in Moscow Journal of Mathematics, and already in this version, my result from previous slides was quoted. Also, approximately at the same time, a third edition of famous book by Richard Guy, Unsolved Problem in Number Theory, appeared. And in this third edition, several new sections were added, and one of them, section D29, was devoted to Diophantine m-tuples. So maybe some of you know that I maintain a web page on Diophantine tuples. In particular, I try to make complete list of references on this subject. At the moment, this list contains 473 titles. I hope it is more or less complete. If you know something which is missing, please let me know. And here you can see the progress during the year. So in 1990, there were only 38 titles. Now we have almost 500 of them. So since Diophantine quintuple conjecture is now solved, we may ask what remains open. There are many remain questions, open questions. One of them is motivated by original result of Bacon and Davenport. So we may say they prove that the Fermat sets cannot be extended to quintuple. But in fact, their result is more precise. As I said, they prove if we fix first free element, then fourth element has to be 120. So I think it is natural to ask, is it true in general? So if we fix free elements, is it true that fourth element is unique? Or at least if we ask that fourth element is larger than the starting free, is it true that it is unique? To state conjecture and to make results, I think first we should say what is 120 in general situation. And the explanation can be done in several ways, but I will quote the result of Arkin, Hogarth, and Strauss, who proved that every triple, so A, B, C, which is good, satisfy condition for triples, can be extended to quadruple. Sometimes in one way, sometimes in two ways. So there are two quantities, D plus and D minus. In case of 1, 3, and 8, D plus is 120 and D minus is 0. So sometimes this D minus is 0, so it does not count as proper extension. And we can characterize this situation. This is exactly the case if triple looks like triple given in Euler solution. So if in some sense is this third element is small as possible, then we have something called a regular triple, and then this D minus is 0, so we may expect to have one extension. But in general, we may expect two extensions, and question is there any other possibility? And all examples, results motivates the following conjecture, that there are no other possibilities, so that all quadruples are what we now call regular quadruples, so that we start with triple, then fourth element should be D plus or D minus, which can be stated in more symmetric way that all quadruples satisfy such quadratic equation. What is known about this stronger conjecture? So let me mention joint work with Attila Petev, when we proved that all quadruples starting with 1 and 3 are regular. This result was generalized by Fujita and together with the partial result by Bijot, Mignot, and myself, where it is proved that all quadruples containing k minus 1, k plus 1, where k is integer greater or equal to, are regular. And concerning general result, I think the best result at the moment is due to Chipu, Fujita, and Miyazaki, when they prove that if we start with the triple, then there are at most 8 ways for joining fourth larger element to this triple. So conjecture is that there is only one possibility, and at the moment we know that there are no more than 8. So this conjecture is still open and I think interesting. So this was brief overview on integer case. How about a rational case? I should say that we don't know any upper bound for the size of rational Diophantine tuples. So we don't know how large they can be, and I think there is no widely accepted conjecture what should be right answer. So let me say what is known. I already said that Euler know one example of rational quintuple, but in fact he found infinitely many rational quintuples. More precisely, he was able to extend every pair with this previous construction to quadruple, integer quadruple, and then this general case of integer quadruples, he was able to extend with fifth rational number. This Euler's construction was generalized first by Arkin, Hogarth, and Strauss. They proved that every triple can be extended to rational quintuple. And I proved in 1997 that every quadruple satisfying one technical condition can be extended to quintuple. These three constructions are almost the same. But this last result has one advantage. Advantage which is especially important if we ask, is it possible to find sextuples? Namely, my construction has some similar feature as the previous construction, which I mentioned, D plus and D minus. And I said in general, we have two extensions, but sometimes one of them provide trivial extension with zero. Situation is very similar here. So again, in general, we have two extensions to quintuple, but if starting quadruple is regular, and Euler's starting quadruple was regular, and Arkin-Hogarth-Strauss quadruple was regular, then one of these extensions is trivial. So they had only one extension, while my almost the same construction provides in general two extensions. What does it mean? We start with quadruple and we obtain two extensions. Altogether, which have 6 numbers, which almost form Diophantine sextuple. Only one condition is missing. The class 2 added number are good if we put them together. And the idea is natural to try to find the sextuples which are really sextuples and obtain with this construction. And first example is due to Gibbs, who found example of rational Diophantine sextuple. So as I said, the problem is to find two extensions of ABCD quadruple such that these two extensions are good if we put them together, so that E times F plus 1 is also perfect square. So Gibbs found some particular example. I enjoyed work with Kazalitsky, Mikic, and Sixai. We were able to find parametric solution. So we proved that there are infinitely many rational Diophantine sextuples. This is the result for 2017. Later, we discovered several different, completely different or similar constructions which provide also infinite families of Diophantine sextuples. Slightly related with the rest of my talk is the following result, joint work with Kazalitsky and Petrichevich. We proved that there are infinitely many sextuples such that all denominators are perfect squares. However, question, is there any Diophantine 7-tuple remains open? I can mention that we know several examples of almost 7-tuples. What does it mean? Almost 7-tuples means that only one condition is missing. But we don't know whether, so we don't have any proper example of 7-tuple, and I don't know what to expect. Okay, so let me come closer to the main topic of my talk to try to explain at least something from the title. So there are several known and I think natural generalization of notion of Diophantine tuple. And one of them is to replace number 1. So in definition, we have product plus 1. To replace this number 1 by arbitrary integer n, say. And for arbitrary integer n, we can define something called Diophantine m-tuple with property d of n, or more shortly d of n m-tuple, or simply d of n set, as I put in the title. So these are set with property that product any two of its distinct elements plus n is a perfect square. So in this notation, our previous classical Diophantine tuples are d of 1 sets. So I put here in brackets a non-zero. So often we request that n is non-zero, since n equals 0 is very different from n non-zero. You can easily see if you put that n is 0, so you ask for sets such that product any two of them plus nothing is square, so you can take infinitely many squares. So there are simple infinite sets with property d of 0. while if you take any non-zero element, then such set cannot be infinite, and quite often it is very small. But for convenience of the end of my talk, I will also speak sometimes of D of zero m-tuples. So sometimes questions when we are low n equals 0 are trivial, but sometimes are non-trivial, and this is why I put also possibility that n is 0 in the definition. So there is very simple result proved independently in 3 papers which appeared in the same year in 1985. Just considering congruence modulo 4, it is easy to prove that there is no D of n quadruple if n is congruent to 2 mod 4. And also a simple result, which I proved in 1993, is that almost converse is true. Namely, if n is not congruent to 2 mod 4 and n does not belong to this set of possible exceptions, then there exists at least one D of n quadruple. For elements of this finite set, the problem seems to be hard and open, completely open until recently, when Boncioccat, Cipu, and Mignot proved that there does not exist D of -1 quadruple, thus solving one of these open problems. And it is easy to see that this result implies also that there is no -4 quadruple. For other elements of this set, problem is still open. How about rational variant of this problem? So it is easy to prove that for any rational number, there exist infinitely many rational D of Q quadruples. I prove it in one conference paper, but recently I was reading again Diophantus' books, and I think it is implicit. This result is implicitly given in one of book of Diophantus. For quintuples, we first had some partial result. For example, we know that there are infinitely many D of -1 quintuples. And the result is related to question whether some elliptic curve has positive rank. And more general result is the joint work with Clemens Fuchs, but we proved that the same, that there are infinitely many rational D of Q quintuples. It's true for infinitely many square-free numbers. And in fact, if we assume parity conjecture for certain elliptic curves, then density of such rationals is at least 1/2. Very recently, young Croatian mathematician Goran Dražić, PhD student of Matija Kazalitsky, considerably improved our result and proved that density of such rationals is at least 0.995. Okay, now the main subject of my talk, which is motivated by following question, which can be found in a paper published by Abdelkrim and Omar Kichel in 2001. They ask, is it possible to find the Diophantine triple, so namely triple with n equal 1, which is at the same time Diophantine D of n triple for some other n? So is it possible that the same set has property for n equal 1 and for some other n which is not equal to 1? And it is somehow natural to say no. And they conjecture that the answer is no, but in fact, the answer is yes. And if answer to this question is yes, then it motivates further questions, and we soon come to some open questions. So here you can see some examples I found very soon after publishing the paper following example, and Zhang and Grossman found this triple. This triple might look familiar. It is sub-triple of this famous Fermat set. So if you take 1, 8, and 100, then we know from Fermat that this is D of 1 triple, but also this is D of 721 triple. So such set exists. So we can be more ambitious. We may ask how many different n's can be such that this set is D of 1, but also D of n sets. So we we saw in the previous slide that we can find one different n. Can we find more of them? And in joint work with Nicola Ajaga, Diana Creso, and Petra Tadic, we proved that there exist infinitely many Diophantine triples which are d of n sest for two distinct n's which are not equal to 1. And we found several, but finitely many examples where we have three distinct n's with n not equal to 1. I will briefly sketch our construction, and here main tool are Diophantine curves induced by Diophantine triples. So such elliptic curves appeared already, and they are very useful, for example, in construction of high rank elliptic curves. Some of current records for certain torsion groups were obtained with similar constructions, with elliptic curves which are related to Diophantine triples. But I will concentrate on their application on this concrete problem. So if we start with the triple as usual, then what we are interested in. So I will change notation. So my number n from previous slide on this and some other proceed slides will be called by x, will be noted by x. Why? To see a more easier connection with elliptic curves, because usually in the equation of elliptic curves we use x and y. So this x, and we can imagine that this is n from previous slides, should satisfy system of this three equations. So this n, ab plus n, ac plus n, bc plus n should be a perfect square. And sometimes it is convenient if you have more conditions which are in sense similar. Similar here means that we have square, square, square always on the right-hand side. Then it is convenient to multiply these three conditions and obtain one condition, one equation. So if we multiply these three conditions, we obtain that some cubic polynomial is a perfect square. This is just an elliptic curve. Since ABC are different numbers, so this is non-singular cubic curve, so this is an elliptic curve. And this connection immediately answers to some questions. So we may ask at the beginning, is it maybe possible to find infinitely many n's with given property? This connection with elliptic curve say no, because we know that elliptic curve can have only finitely many integer points. So there are finitely many x's here, and this means finitely many n's in our original problem. But how many n's we can find is still interesting question. So this elliptic curve has some more or less obvious points. Some of them are not useful to our problem, but some of them are crucial to our solution of our problem. So some obvious points, but not very interesting, are points which correspond to zeros of this cubic polynomial. So we can easily see that it is factorized in three linear factors. So each linear factor has a root. So we have 3 points, but these points are of order 2, and we will soon see that points of order 2 are not interesting to our problem. But there are 2 other, I think, obvious points. If you put x equals 0 here, you will get a square, b square, c square. So there is a point with first coordinate 0. And all these mentioned points until now has nothing to do with Diophantine triples. But since we started with Diophantine triple, then there is additional point. So we may take x equal 1, because ABC is Diophantine triple. So there is a point with first coordinate 1. So let's fix some notation. I will denote by ABC these 3 2 torsion points, for which I announced that they are not interesting, but points with first coordinate 0 and first coordinate 1 are interesting, and I denote them by P and S. And let's come back to this slide. So we multiply these 3 conditions and we obtain an elliptic curve. So question is, can we go back? It is clear if you multiply 3 squares that you will get square. But you can multiply with 3 numbers which are not squares and you obtain square. For example, you can multiply 2, 3, and 6. and you will get square, and no one of numbers 138 is a square. So we can ask, if we study this elliptic curve and find something interesting here, which points here really satisfy original system star. And solution is given here. It is well known, sometimes called two-decent proposition, which says that solution of the original system, so points on the elliptic curve of which each of these three factors is a perfect square, are exactly points which are, we may say, double points. So points of type 2 times something, but this 2 times something mean addition on an elliptic curve. So I am somehow assuming that we are familiar that on each elliptic curve we can introduce addition of points by a second and tangent law, and this 2 times something means addition of points to itself. So by taking tangent line on this point. So what we are really interested in are points which satisfy 2 conditions. So first, they are of this type, 2 times something, and second, they have integer coordinates. And each problem separately is more or less well understood. But these 2 problems together leads to some unknown area, I would say. It is not clear what to expect here. And this is why I think our result is first step in study such things. So first, let me notice that we know one solution. So x equal 1 is solution. It is trivial to notice that it is solution, but let us somehow interpret it in this new situation. So if this is true, and it is certainly true, then S should be 2 times something. This is not completely clear or obvious, but one can easily check that S is indeed 2 times something, and this is a point which I call it R. So we are interested in doubles of points. So if we start with points of order 2 and double them, we get neutral elements, so we can ignore A, B, C. So what remains are point P and S, and in general, they will be independent points on infinite order. However, if we take C to be simple as possible, as in example of Euler, which we already said we will call such triples regular, then these 2 points are dependent, and we will, in the rest of next few slides, try to avoid this situation. So we will consider triples which are not regular. Okay, so what we want to consider are some simple linear combinations of point P and S. And since S is already double of some point, here coefficient can be arbitrary, but P is not of that shape, so coefficient in front of P should be even number. Why I said simple combination? Because anyone who has experience in computation with elliptic curve will say, if you take a large coefficient here, it is very unlikely that you will get integer point. So if you start with integer point, then after few iteration, denominators appeared, and then these denominators grows very fast. We can say something about this, but it is not relevant here. So let's take some simple linear combination. The simplest one is probably to take point 2P, and it almost gives a starting point for our solution. So first coordinate of point 2P is almost an integer. So here we can see 4 in the denominator. It means that if A plus B plus C is even, then this is integer, and we obtain one required n. It remains to consider question, is it possible that n is 0? And it is easy to see that it's not possible. And also, is it possible that n is equal to 1? And one can show that this is equivalent to the ABC to be regular triple. So this is reason why we omit this regular triples. So we have this starting result. If we have any triple which is not regular and such that A plus B plus C is even, then there is one additional n different from 1. So how about other simple linear combination? We took some computer search for points of the form S plus minus 2p and 4p. And for two of them, S minus 2p and 4p, we never find any solution, any integer solution. While for point S plus 2p, we find many solutions. Some of them are listed here. And already here we can notice some regularities, probably. And this somehow indicates that it is likely that there are infinitely many solutions. And in fact, we prove it. And how we prove it? So we analyze these numerical examples. We notice that all of them satisfy additional condition, that this x coordinate is in fact equal to a plus b plus c. So we analyze this condition. This is some equation in ABC. We factorize this condition, and we obtain three factors of different shape, different properties. So first of them is equivalent to condition that ABC is regular. So we already said and argumented that this is another argument to avoid regular triples. We showed that this third equation has no solution. So what remains is Q2. Q2 is some symmetric quadratic equation which looks like equation for regular quadruples. And it is exactly condition. So if we solve this condition to C, we get expression which is exactly condition that A, B, C together with number 2 is regular Diophantine quadruple. It remains to check some technical condition, whether numbers obtained with this construction are indeed different and different from 1, and everything was checked. So what we proved, that if we have any triple A, B, C, which together with number 2 forms regular Diophantine quadruple, then this triple is also D of n triple to 2 distinct n's with n not equal 1. Here are some explicit construction. Maybe not so interesting, but just to say that everything can be written in a very explicit way. So we may start with 2 and something, and this sum plus 1 should be squared, and this A should have this shape. Then we can use Euler's construction to find third and fourth element, and then our construction produce 1 and 2 elements which are not equal to 1. Other explicit construction is to take 2 and some concrete number which is good with 2. For example, 2 times 4 plus 1 is a perfect square, of course. So if we take 2, 4, and then try to find third element, then we have to solve some Pellian equation, and all solution of this Pellian equation satisfy some recurrence. And then it is not hard to show that if we take 2 successive elements in this sequence, then they are good together. So again, we have some explicit construction of Diophantine triples with given property. For more than 2 n's, as I said, we don't know other infinitely many such triples. Here are all explicit examples which we know. So if one can see some regularities, this is good idea for research, I think. So we started with the D of 1 tuples. So we may ask, if we omit this condition that one of these n is equal to 1, is the situation different? And the answer is yes, it is very different. In this case, a number of such n's can be arbitrarily large. So if we fix n equal 1, then we know examples with other 3 or 2 or 3 other n's. If we omit this condition, then this number can be arbitrarily large. It is easy to see, and I will provide one example in next slide. It is enough to start with any triple which produce elliptic curve with positive rank. If we have positive rank, then we have infinitely many rational points. If we have infinitely many rational points, then we have also infinitely many double points. Just double any of these points. And then we can take, say, first 100 points. And what will we have? We will have n equal 1 and 100 rational numbers. If we get rid of denominators, we will obtain 100 integers. But since getting rid of denominators means multiplying all numbers, this starting number 1 will not be anymore number 1, because this number 1 is also multiplied by denominator. Perhaps it is better to consider one concrete example. I will again take this subtriple of Fermat, 1, 8, and 120. It induces elliptic curve of rank 3. And so it means it has infinitely many rational points, but in particular, it has several simple rational points. So I will not take 100, as I said in previous slide, because it is hard to present. I will take 5 points, but I think you will see my point. So here we have 5 points, but only 2 of them are integers. These are integers 1 and 721, which we already saw. It is in the work of Zhang and Grossman. But there are additional 3 simple rational numbers, which if we multiply by 6 squared, they will become integers. What does it mean, multiply by 6 squared? It means the starting triple should be multiplied by 6. So starting with 1, 8, and 120, we obtain triple 6, 48, and 720, which is D of 1 set for these 5 numbers. And with same construction, we can get this list as large as we wish. So this was about triples. How about quadruples? If you ask me some years ago, I will say no way that there is this quadruple which is good for 2 different ends. But my colleague Vinko Petricevic is very good in computation, and he found many interesting examples of objects for which I didn't believe that they exist. Some of them we were able to explain, and this is one of such examples. So we prove that there are infinitely many essentially different sets of quadruples, which are D of n1 quadruples and also D of n2 quadruples for 2 distinct not zero n's. Our construction was motivated by his examples, in which we noticed that many of them has property that 2 elements, say A and B, are such that A over B is equal to -1/7. Then we analyze such examples and noticed that there are some regularities here, and I will skip some technical details. So using this assumption of regularity, which reduce significantly number of conditions, then this -1 and 7 help us to obtain then several remaining conditions and effect equivalent. So at the end, we finish with a small number of conditions, and we were able to satisfy parametrically. So we have 2 parametric families of quadruples, which are D of n quadruples for 2 different n's. And moreover, by using Pellian equations, we were able to prove that there are infinitely many examples in which you can take A to be exactly -1 and B exactly 7. Here you can see starting list of such examples. Another very similar result, but in some stronger, again with Vinko Petricevic and with help of his examples, is this strange quadruple. You should not read all coefficients here, but I think you can see here something that all these factors are squared. So it means A, B, C, D are squares. So this A, B, C, D has the same property as before. So this A, B, C, D is 2n something quadruple and also 2m something else quadruple, but also this is D of 0 quadruple, because all elements are squares. So it means if you multiply them, increase by 0, you will also obtain squares. So if you have just condition D0, it is trivial. But if you combine it with already non-trivial additional conditions, I think it produces some interesting result. Just few words on construction. So we use something which I will also say that does not exist, but now we know that it exists, and there are infinitely many examples of so-called doubly regular quadruples. So what is a regular quadruple? It was already written, mentioned in a few slides. So ABC is regularly satisfy this quadratic equation. But if the same quadruple is also D of, say, x squared quadruple, then we can divide each element of this set by x, and we will obtain D of 1 quadruple. And we may ask, is it possible that this new quadruple is also regular? Sounds strange that such thing exists, but we proved that it exists. So first, it was convenient. If it exists, it is convenient to our problem, because it leads immediately that ABCD is x squared, which with some manipulation immediately imply that all these products are squares. So if we obtain such example, we will get D of 0 almost for free. So actually, question is how to find this doubly regular quadruples. We use some parametrization, novel parametrization of D of 1 triples. In some sense, most symmetric is due to our colleague Luka Lasic, but we here use some slight modification. Then we compute D from regularity condition, and it remains condition that ABCD is x squared, which can be expressed in terms of elliptic curve over a rational field of rational function. And we analyzed this elliptic curve. We found that it has a point of infinite order. Simple points on this elliptic curve unfortunately produce some trivial examples. So first, on trivial example is this huge formula, which I don't want to present you anymore. But I will finish with the last word in my title. It is quintuples. So how about quintuples, which are good for two different n's? Here we have example only in case that one of these n's is 0. So we have examples, infinitely many examples of quintuples, which are D of 0 quintuples, but also D of n quintuples for some n not equal to 0. Again, starting point is a concrete example found by Viko Petricevic, but after that, Matija Kazalitsky analyzed these and some other examples, and we proved that there are infinitely many such examples. Here we need some additional name, because I use regular and double regular and something else. So we choose the name exotic. Quintuple, for quintuple satisfying this condition that ABCD is equal 1, and that this quintuple contains two sub-quadruples which are regular, and that product any of its elements is perfect square. So I think exotic maybe is not a bad name for such structure. A starting point is explaining, say, exotic quadruples. So what are quadruples? How look quadruples satisfying ABCD equal 1? It is easy to parameterize them. And from this parameterization, we see that some of conditions are again obtained for free. So any product in this quadruple is perfect square. So what remains is this fifth element. Regularity conditions leads to some equation, and we can solve it for S. And then, as I said, it remains just condition that one of the elements in quadruples times fifth element is square. This is complicated condition, but it leads to consider several genus 0 curves. I put here one example, and it is well known if we have one point, rational point on genus 0 curve, then there is parametrization of this curve. And if we put this particular parametrization back in this condition, we obtain that something is equal square, and this something is quartic polynomial. So we may expect that it is birationally equivalent to an elliptic curve if it has rational point, and there is a rational point on this curve. And the last question was whether this elliptic curve has positive rank. Fortunately, it has a rank equal 1, so it had positive rank. So there are infinitely many solutions, and the simplest solution is the one from which we started. So these numerators are exactly from our example, but if you want integers, then we multiply everything by this number in the denominator. So we change d of 1 to d of something else quintuple. And last question, last slide, motivated with this example and maybe with some previous result of sextuples when we have squares in numerators. Here we have squares in denominators. We may ask, is it possible to find quintuples where all elements are squares? So d of 1 quintuple with all elements squares. I don't know the answer, but let me just say two things. So we know that there are infinitely many quadruples with this property, and these quadruples are obtained from this exotic quadruples and proposition describing them. So at some point, all our examples fit in this proposition. So we thought maybe this is idea how to prove that there are no such elements. Because if A, B, C, D is equal 1, and you have fifth element E, then A, B, C, E cannot be the same. So it cannot be 1. But now again, Vinko found, make the experiments, and now we have one example where the product, so all elements are square, but product is not equal 1. So I should say that this question is completely open, and I don't know how to attack it. Thank you very much for your attention, and best wishes to Michel.
Yeah. Thank you so much, Andrej. And I'm sure there will be plenty of questions because this is a very popular area, but we can certainly pick up a few of them. So is there any question in the, yes, so Krishna will have one.
Hi, sir. So I was, I have sort of an open-ended question in that, so all these things you're dealing with integers, right? You're taking the squares of integers, you're adding integers. And if you go to a number field, you have the notion of the ring of integers, but things are not quite like the integers that we have. So my, sorry, my question is that if you go to the ring of integers and consider all these operations using ideals, you take a square of an ideal, you add two ideals, and you ask whether what you're getting is another square of an ideal. So Diophantine tuples where integers are replaced by ideals rather than the integers from the ring of integers. So is that an easier or a harder question? Is that been considered by someone? And yeah.
Okay, so as far as I know, not in this formulation as you asked. So problem was studied for ring of integers in a number of fields, and in fact, the next talk we'll discuss D of 1 version of this problem. So probably also some other information you will see here. So what was considered was the problem of this size, how large such set can be, and also what was considered was generalization of this, what I said, very almost trivial result, that if n is congruent to 2 mod 4, then there are no D of n quadruples. So this problem for which number there exists a quadruple in several structures, quadratic number field, cubic, some big quadratic, and I think it is very interesting to consider this in any structure where this problem makes sense to characterize these numbers. And at the moment, it seems that always the result can be stated in this form. Quadruples does not exist if a number cannot be written as difference of two squares in the corresponding ring. Because in integers, the numbers of the form 4k plus 2 are exactly numbers which are not difference of two squares. It is not clear whether this connection is direct. It will be nice to see direct connection between these two problems, because all the results that I know consider these two problems separately. Solve problem of representability of difference to two squares, maybe it is already known, then solve this problem of quadruples and compare them, and they are always same, or there are maybe finitely many possible exceptions. So this is what I know, but this version I didn't see that it is say considered as far as I know.
Okay, sir. Thank you.
Thank you.
Yeah. So is there any more question? Okay, Vishwanathan has one.
Yeah, hi.
Hi.
Instead of looking at AB plus N, can we look at A square plus B square plus N and ask the same question?
Sorry,
No, so
can you repeat?
Yeah, so the question was, if you have a tuple such that, whether you have a tuple such that the product of any two translated by some N is a perfect square, right? So instead of that, can we ask A square plus B square plus some N is a perfect square? And
Probably we can consider this problem, but I don't have in mind something which I can quote. A version of this problem was considered, I think, by Katalin Jarmati and Jan Bijot, but I cannot say immediately which version. So it was something by sum of squares.
yes.
And they compare it with this problem, but
The reason I ask is, isn't that like quite natural? Given any tuple, is any two of them part of a Pythagorean triple? I mean, rather than asking AB plus.
it sounds natural, but I cannot say immediately to which problem it
And the reason I ask is, the moment you said AB plus 1, I got reminded of this very famous Olympiad problem, which says AB plus 1, if AB plus 1 divides A square plus B square, then the ratio is a perfect square. So, I mean, if you...
Yes, I know that.
Yeah. So...
that problem, yes.
So that, anyway.
It's Olympiad problem, yes. But I cannot say, so maybe later I can find some reference and send you, but at the moment, whatever I said will be probably imprecise.
Yeah. Thanks a lot, Andres. So now this is online participants. If you have any questions, please raise your hand and you can unmute yourself. So we can open the chat box. So Andres, maybe you can open the chat box, maybe.
Yes.
Can you see that, Andres?
Can the concept of Diophantine tuple be generalized to any power? Okay. So it is generalized to powers. So one can consider, there are two, say, variants, at least two variants of this problem. So you can fix power, for example, cubes or some kth power, and consider how large such can be. And this is considered in some sense solved in some sense in joint work with Jan Bijot. We used results of Tarlok-Shori, and we prove quite strong result that if K is large enough, and this is explicit, 100 and something, then such set cannot be have more than 3 elements. And for small case, we obtain some bounds which are not best possible, but reasonable. And also, I see here a variant saying that sum is a perfect cube. So I don't know for this variant, but the problem which was considered and is considered that all sums are squares. This is interesting problem, and I think examples are known of 6 tuples or something like that, and also no absolute upper bound is known. What is different if you consider some or any problem which is in some sense homogeneous? So in this original problem, you have AB plus 1. So AB is of, say, degree 2 and 1 is of degree 0. So if your problem is not homogeneous, then integer and rational case are very different. And if it is homogeneous, then they are in some sense equivalent. And it means that they are both hard. So a rational version of any problem which leads to elliptic curve with positive rank is hard. And the integer case can be simple sometimes, or at least reachable. So this is different of this, the difference of these two kinds of problems.
Yeah, thanks a lot, Andrej. So I don't see any more hands raised. So I have a very simple thing, Andrej, to ask, which I was thinking for some time. So there are no quintuples, integers in a Diophantine over. And as far as I know that in the ring of integers, as Krishna was asking, the standard one, not the ideal version, the standard one as you consider, that take integers, take the product and sum with something 1 or so, please square again in that thing. So I was thinking that what is your expectation? Like, I know there is something like one of my students whose talk will be next, who is working in the, what is the length of this Diophantine tuple possible? So it's like 36 or so. I mean, I don't know, not exactly that. Yeah. So that's not expected. So do you expect a quintuple there in Z square root of D, let's say, in the ring of integers of quadratic field?
So this depends on D. So for example, I told you that sometimes this D plus and D minus, we have two different extensions. And since there are no quintuples, we know that they are not good together in integers. So D minus times D plus plus 1 is not a square of integer, but it is integer. So if you consider a square root of this integer, this number will be square in this quadratic number field. So certainly there are quintuples in certain number fields.
Okay.
But this is what some trivial, say, result or straightforward result. But I don't know what to expect better than this. So I heard very general conjecture, I think due to Attila Pete, who predicted that absolute upper bound should exist for number fields, and it should depend only on degree.
Okay, yeah, that's expected, but at least thinking about quadratic fields, I mean, certainly for number field, like I remember, so I had this idea of extension, like let's say ABC is a integer Diophantine tuple here, and then I say that it is an extension, let's say in Z square root of D, if I find an A plus B square root of D, so that, you know, this ABC and D, D plus, something square root of D becomes a quadruple there. So I remember one of your work where I think the format triple you have done in ZI or something like that. You have defined a similar kind of an extension, and you have showed that you can lift it kind of thing in some way to ZI. So I was thinking that is it so that's the definition that I'll call it a lifting of quadruple, let's say in Z to Z square root of D, if I have a plus B square root of D such that A, B, C and that particular non-trivial number from Z square root of D becomes a 4 tuple and quadruple or quintuple there, and try to solve that equation. Because I know that the first 3 satisfies the condition, whatever the Diophantine condition is required. So the 4th is unknown. So what kind of D or what kind of, discriminant that would be true? So I was asking, but I saw your paper, in archive maybe that for ZI. So this format triple, you were trying to lift and you were calling such an extension, something like that. So maybe that could be a way. So yeah, I'll be in touch with you, that particular.
This sounds interesting, but I should write down on paper.
Yeah, sure. We'll be in touch. Thank you so much, Andrej. It was a very interesting talk, and the results are very, very interesting, especially the elliptic curve version of that one, and then all those results getting in terms of the properties of elliptic.